In today's session, we'll discuss on what is 0-1 knapsack problem. And I'll try to work out and show you how a given 0-1 knapsack problem can be solved using a dynamic programming approach. So we have discussed regarding knapsack problem already, while we have discussed and studied greedy algorithms. So a knapsack problem can be stated like this. You'll be given a knapsack, a bag with some capacity M. So the knapsack bag will have some maximum capacity M, and then you'll be given a set of objects x1, x2, x3 and so on up to xn. You'll be given a number of objects. Each object will be associated with a weight W, and each object will be associated with a profit P. So for some object number xi, its weight is Wi and its profit is Pi. As such, all the objects will be associated with their respective weights and profits. Now, the challenge is that you can fill all these objects into the bag. If all of them fit into the bag completely, put all of them into the bag and you can earn the profit. You can earn the maximum profit. But given that all of the objects will not completely fit into the bag because there is a maximum capacity associated with the bag, then you'll have to use some technique and you have to select a few objects that can be kept into the bag. And whichever objects are selected, those objects' profit will be earned. Now, whenever you are making a decision on an object, whether you want to put it into the bag or you do not put it into the bag or so on, you'll be having three possibilities. Given an object xi, you are going to completely put this object into the bag. That is, if this xi has some weight Wi and this complete weight of the ith object completely fits into the knapsack, then you can decide that this ith object can be completely kept into the bag, which is represented by a value 1. A value equal to 1 indicates that ith object is decided to be completely kept into the bag. A value of 0 indicates that you have decided not to include ith object into the bag. If only these two options are available, either you can fill the object into the bag completely, or you have not selected to put the item into the bag. There are only two options: no filling represented with 0, fill the item represented with the 1. If only these two possibilities are available, then such a knapsack problem will be called as 0-1 knapsack problem. So this is the type of knapsack problem that we are going to discuss now, and we'll see how it can be solved by using dynamic programming approach. So we'll have to take some number of decisions. If there are n objects, then I have to make a sequence of decisions on all the n objects, and in each step I'm going to make one decision on one object. Now, the sequence of decisions that I'm going to take, assume that I am making decisions in the order xn, xn minus 1, and so on up to x1. That is, I'm first taking a decision on the nth object to keep it into the bag, or I do not want to keep it into the bag. I'll make a decision on the nth object first. Then later, I'll make a decision to include or not to include n minus 1th object into the bag. And so on. Finally, I'll make a decision on whether I'll include the first object into the bag or not. So this is the sequence of decisions that will be made in using dynamic approach. So first step 1, you are going to make a decision on nth object. Now there are two possibilities. I'll decide that I'll not include nth object into the bag, that is represented with the value 0. If such is the case, then the remaining capacity of the knapsack will remain as M itself, because I have not included the object into the bag. The remaining capacity of the knapsack will stay as it is without any change. And also, I am not going to accumulate any profit Pn. Pn is the profit of Xn. So I'm not going to accumulate any profit Pn because Xn is not included in the bag. Then the second scenario, I have decided that I'll include nth object into the bag, which is represented by using n value equal to 1. Then if I have kept an object, nth object into the bag, then the capacity, the remaining capacity of the bag changes. Now I'll have to update what is the remaining capacity of the bag. I'll also have to update what is the profit earned till now. And for that, this is the formula for updating the remaining capacity of the bag. This was the current capacity. And after including nth object into the bag, the remaining capacity of the bag will be M minus Wn. And if I've decided that nth object will be included into the bag, then its profit should be earned. So I have earned a profit of Pn. Right now, if this problem is satisfying the principle of optimality, then it can be solved by using dynamic programming approach. So if I say that 0-1 knapsack problem satisfies the principle of optimality, that means once I have made a decision on the object xn, then the next two states, next possible state can be either first state or the second state. Okay, I have made a decision on the nth object. Now I have to make decisions on the remaining objects starting from xn minus 1 to x1. I have to make remaining decisions on all these objects. Then once I have made a decision on nth object, then the remaining decisions must also be optimal with respect to the decision made on xn. If this condition is satisfied, then we say that 0-1 knapsack problem satisfies the principle of optimality. Because this problem satisfies this principle, hence it can be solved by using dynamic programming approach. Now, when I'm saying that some state is there after making a decision, there is a possible next state. Let us assume that the next state after taking a decision, the next state is represented by fi of y. Because to solve an knapsack problem, you'll have to go through n number of steps. So at any step where you're trying to make a decision on ith object, whether to include ith object or not, this is the ith step where you are taking decision on ith object. Y is the remaining weight of the knapsack. Now, your algorithm NAP will decide whether ith object will be included into the bag or not as per the remaining weight of the knapsack Y. Now, how that decision is made? You have to use this formula. This is the condition. Okay, this is the current optimal solution that you have to determine. Fi minus 1 of Y. This was the decision made in the previous step. I minus 1th step, I have made some decision, I have come up with the solution, and this is the solution from the previous step. This is the solution, optimal solution from I minus 1th step from the previous step. Right now, this is ith step. Now in ith step, I have to make decision whether I have to include this ith object into the bag or not. And for that, I have to check what was the optimal solution in the previous step and what was the profit earned. And if I include this ith object into the bag, what will be the profit earned? These two values I am going to compute. What is the profit earned in the previous step? And what is the profit earned if I include ith object into the bag? Now, within these two values, whichever is giving me maximum profit, that I am going to take it as the optimal solution from the current step. So here Y minus Wi is, if I include ith object into the bag, its weight will be reduced, remaining weight of the knapsack will be reduced, so that will be Y minus Wi. And if I include ith object into the bag, some profit Pi will be earned, so it will be plus Pi. So this is before including ith object into the solution, what was the profit? And if I include ith object into the solution, what will be the profit? These two values I'll take, compare, and whichever gives me maximum profit or whichever gives me optimal solution, that I'll take it as current solution. And I'll move on to the next step. The next step will be I plus 1th step. And this process will repeat for n number of times because there are n objects. Now, at some point of time, you'll have to start at 0th step. So that will be f0 of y, which is equal to 0. You have to start with a 0 value and continue with f1, f2, f3, and so on. Now, for finding this fi of y, which is given a knapsack capacity of y and an ith object, you are going to find out an optimal solution by deciding whether this ith object will be included into the bag or not. So for finding this, you will have to find some point. You have to start with f0 of y or f0 of m, where m is the maximum capacity of the knapsack. I'll start here. Then from f0 of m, you are going to find out f1 of some y. Then from there, you'll try to find out some f2 of some y2, and so on, up to you'll find fn, where the knapsack capacity is either fully filled or there may be some remaining capacity may be there. You are unable to fill the knapsack fully. So this is the process. Now, for finding this optimal solutions at each step, you have two methods. One is called as tabulation method. The other one is called as set method. Now here I'm going to discuss the set method for finding optimal solutions to the given 0-1 knapsack problem. For that, you already know that there will be a few, there is a set, and each of this f function is represented by a set S1. F naught is represented by a set S naught. F2 will be represented by a set S2, and so on. Now, what is this each set contain? Each set, as you know, represented with curly brackets, it will contain set members of the form P, comma W, until there will be P1, comma W1. This is a set member. Comma, I'll have P2, comma W2, and so on. So as such, each optimal solution of the knapsack problem is represented by a set, and each set will contain members, and each member will be of the format P, comma W, where P is the weight, P is the profit, W is the weight. Now, we'll try to solve a problem. Then we'll get into the details of the algorithm. Have a look at the given problem. So given an instance of 0-1 knapsack problem, where the maximum knapsack capacity is 25. There are 4 objects that are given, and each object has with it an associated profit and weight. There are 4 objects. So these are the profits of the 4 objects and the weights of the 4 objects. Now, your challenge is to use a dynamic programming approach and find an optimal solution for the given problem. And for this, we are going to apply dynamic programming approach using sets method. So this problem I'm solving using sets method. So I'm going to tabulate all the information here. There will be 3 columns. You have this selected object. I'll go in the order as per the order given in the problem. First object, second object, third object, and fourth object. I'll go in the same order. In each step, I'm going to make a decision whether I'll include the object or not into the bag. And for that, before making those decisions, because there are 4 objects, I need to take 4 decisions, whether to include each object into the bag or not. And for that, as I said, we'll make decisions in the reverse order. First, I'll make a decision on 4th object to include it into the bag or not. Then I'll make a decision on 3rd object. Then I'll make decision on 2nd object. Finally, I'll make decision on the 1st object in that order. Starting from nth object to the 1st object, I'll make decisions. Now, before making the decisions, I'll be needing some sets. I'll have to formulate some sets, and those sets are S0, S1, S2, S3, and S4. These sets I'll be needing for making the decisions. So I will first prepare all these sets. Then using these sets, I'm going to make decisions on each object to include the object into the bag or not. So this is the process for preparing the sets. I'm going to prepare set 0, set 1, set 2, set 3, set 4, and so on. Up to where I have to go on preparing these steps, sets. Why I have stopped at S4? Why did not I prepare set S5? For that, check how many number of objects are there. Accordingly, you'll stop because there are 4 objects that are given in the problem. I'll prepare sets up to S4, maximum up to S4. So let me get into the process. Always S0 starts with 0, 0. This is the member of a set. So as I said, each set will contain members. So a set is represented in curly brackets. S0 is a set. It will contain members and each member will be in the format P, W. Profit, weight. Now, initially, profit and weight will be equal to zeros. So I have started by taking S0 equal to 0, 0. So I have taken S0 equal to 0, 0. This will be S0 preparation will be same for any given problem. You have to always start with 0, 0. Then from 0, 0, you are going to add the first object P, W. This is P, W for the first object. Right? So now you are going to add S0 with this first object. You are going to perform addition. And you are going to get this value. Now for this 0, 0, I am going to add it with 2, 10. And the value I am going to get is 2, 10. Now, the next thing that you have to do is, you will have to merge. S1 will be equal to S0 union. You are going to merge S0, 1. These two things you are going to merge. That is, you are going to merge S0 with S0, 1. You know union operation on sets. So that is going to give you something like this. So let me so after merging, I'm going to get 0, 0. And another member I'm going to get 2, 10. I'm going to get these two members in this set. Now I have prepared S1. Now what is the meaning of this set S1? There are two possible states. After making a decision on first object, there are two possible states. 0, 0 is the state when I have taken a decision. I'll not include first object into the back. 2, 10 is the state which represents if I include first object into the back. 0, 0 represents the state where first object is not included. 2, 10 indicates the state when first object is included into the back. Now S1, then I'll go to S2. Now S2 will be equal to, I'll get S11. I'm going to prepare S11. For that, what I should do? I should take second object profit and weight, 5 plus 15. and I have to add this P comma W to every member in S1. So that is, I have to perform addition 0, 0 plus 5 comma 15. So that will give me 5 comma 15. Then I have to add 5 comma 15 to 2 comma 10, and that is going to give me 7 comma 25. Once S11 is ready, you are going to prepare S2 by merging S1 with S11. S1 merge with S11, you are going to get S2. And S2, if I start writing, merging, so 0 comma 0 will be there. Then 2 comma 10 will be there. 5 comma 15 and 7 comma 25. This is S2. And you have to remember that whenever you are merging and writing, you have to always write the members in the order of their profit and weight. So these are your profits and weights. This is profit weight. This is another profit and weight. This is another profit comma weight, and so on. And whenever you are writing these things, you have to write them in the order of their profits, increasing order of profits, then increasing order of their weights. And why I'm saying this is, whenever you have merged, you are going to apply two rules. You are going to apply two rules for performing a process which is called as purging. After merging, you have to perform purging, and purging is the process where you will try to eliminate non-feasible solutions. You'll try to eliminate non-feasible members. Now, the first rule is that a solution is feasible if a solution is feasible if the total weight is less than m, is less than or equal to m. Now, for this, check any of this member, check the weight. The second value in each member is the weight, P comma W. So second value is the weight. Now check this. The capacity of the bag, the maximum capacity given in this problem is 25. So if any set member has weight more than 25, you can remove it, because you cannot fit an object with capacity more than 25 into the bag. So check, this is a 0 less than 25, 10 less than 25, 15 less than 25, 25 less than or equal to 25. So all the members are feasible. So first rule, first purging rule, I have checked. Then next thing that you have to check, you have organized these set members in increasing order of their profits. So for that, if you check, you can see here I have written them in order. 0 is the profit, which is less than or equal to 2, which is less than or equal to 5, which is less than or equal to 7. So all these set members, I have ordered them in increasing order of their profits. Profits are increasing. Now, weights also should increase. That is the dominance rule. Weights should also increase. Profits also should increase. Weights should also increase. So you can see here 0, 0, 2, 10. If I consider these two as a pair, profit is increasing, weight is also increasing. Fine. Next two members I'll take 2, 10, 5, 15. Profit is increasing, weight is also increasing. Fine. No purging is done. 5, 15, 7, 25. These two I'm going to take. Profit is increasing, weight is also increasing. So I have not done any purging here. All the members are feasible members in the solution. So I'll go with the next step. From S2, I have to generate S21. So how can I generate S21? I have to add third object to every member in S2. Third object P, W, add it to every member in S2. So I'll start adding. I'll have to add 8, 6 to 0, 0. I'm going to get 8, 6. Then next set member I'm going to take. I have to add 8, 6 with 2, 10. So if I add, I'll get 10, 16. Then I'll add 8, 6 to 5, 15. So I'll get 13, 21. Then finally I'll add 8, 6 with 7, 25. That gives me 15, 31. Now I'll start merging. To form S3, I'll have to merge S2 with S21. S2 with S21. These two I have to merge. And while merging and writing, I have to write them in the order of their profits and their weights. So I'll start writing. First, I'll write 0, 0. Then I'm going to write 2, 10. Then 5, 15. 7, 25. 8, 6. 10, 16. 13, 21. And finally 15, 31. Right? So these are the things that I have. Now you apply. Any member whose capacity, whose weight is more than 25, you can remove. So for that, I'll check weight values, P, W. So in each member, second member is the weight. So you can see 0, 10, 15, 25, 6, 16, 21. All these weight values are less than 25. But you can see here there is a 31. 31 weight is more than 25. So anyway, this member, if I keep it, it will not give me a feasible solution. A solution is called feasible if it does not satisfy, it satisfies the maximum weight of the knapsack. So I'm going to remove this. I'm going to perform purging. Purging is where I'll check all the members. If any of the member is violating the maximum capacity of the knapsack, I'm going to purge it. I'm going to remove it. Now, that was the first purging rule. The second purging rule, you have to check that all the profits are anyway increasing because I have written them in the order of their increasing order. Profit increasing order lone sets I have written. You have to also see that weight should also increase. Between any two members, weights should also increase. Weight should not decrease. Then in such scenario, I'm going to perform purging. This is second type of purging. For that, check two items at a time, 0, 0, 2, 10. Profit is increasing, weight is increasing, okay. Then next two set members, 2, 10, 5, 15. Profit is increasing, weight is increasing. Then these two, 5, 15, 7, 25. Both profit and weight are increasing. Now I'll have to compare 725 with 8, 6. 7, 25, 8, 6. Now, if I check that, profit is increasing. Profit was 7. Next, it has become 8. So, profit is increasing. But you can see that weight is decreasing. Whenever you have such pair where weight is decreasing, you are going to purge the first one. You are going to purge the first one. So, I'm going to remove 7, 25. Now, I'll have to compare 5, 15 with 8, 6. These two are the adjacent pairs now. 5, 15, 8, 6. Again, it's violating the rule. Profit is increasing, but weight is decreasing. If weight is decreasing, I'm going to perform purging 5, 15, I'll remove. Then, now, 2, 10 and 8, 6. Now, these became adjacent. 2, 10, 8, 6. These two have become adjacent. Now again you can see that I have to again perform purging because weight is decreasing. So I'm going to purge 2, 10. Now you have to check 0, 0 with 8, 6 because now this has become adjacent. These two have become adjacent. 0, 0, 8, 6, both profit is increasing, weight is also increasing. Now it is fine. Now compare 8, 6 with 10, 16. Okay. 10, 16 compare with 13, 21. This is also fine. So what are the things that you have got? Finally left out things. I'll remove this one. All the purged items I'll remove. I'll remove 2, 10. I'll remove 5, 15. And I will remove 7, 25. So this is your S3. S3. This is your S3. Now, I'm going to calculate S31 and S4. Right? So